Hello guys, this is CodeNCode and this is video editorial for the problem LCM Sum taken from SPOJ. So the problem is very simple. You are given n and you have to calculate this sum. The sum of LCM of 1 comma n plus 2 comma n plus 3 comma n dash 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 n comma n, and this is the expression that we have to evaluate. Now, of course, the definition of LCM is given here. Now, the basic approach using which you can calculate this, the super naive approach would be to actually do this, calculate LCM of each pair and then add it and print the solution. This would require n log n time, because log n factor, because of the calculation of GCD. To calculate LCM of a and b, as we all know, is a times b divided by GCD of a comma b. Now GCD function takes log n time. That is why to evaluate this whole expression would require us using naive approach. Naive approach would require us n log n time, and the purpose of this video is to explain you an approach using which you can calculate or answer each query in constant time. Of course, we need some pre-processing time. I think the overall pre-processing time is n log n, and after the n log n pre-processing time, there are these many queries, and each query you can answer in big O of 1 time, that is in constant time. Whether if you use instead if you use the naive approach, each query would require n log n time, where n can be as large as 10 to the power 6. So of course you can't answer 3 into 10 to the power 5 queries if you use n log n approach. So these are the test cases. There are 3 test cases. In the first test case, n is equals to 1, answer is 1. In the second test case, n is equals to 2, answer is 4. N is equals to 5, answer is 55. So these examples you can go through yourself. Now let's go directly jump into the conclusion, and let's directly jump onto the solution, how we are going to build the solution. Now see, this is what we have to calculate. S represents the total sum that we need to calculate. S is equals to sum of LCMs 1 through n with n, right? Now we all know that LCM of n comma n is n actually, so I'm sending n to the left hand side, and the right hand side I'm only having these expressions till n minus 1, right? Now if you reverse these terms, what will happen? This is what is gonna happen. Nothing special. I've just reversed the expression, so I'm starting from n minus 1 going till 1. Now if you add these two expressions, this expression and this expression, or these two equations, this is what you are gonna get. 2 times s minus n is equals to LCM of n minus 1 comma n plus LCM of 1 comma n. So you see, these two are together, plus LCM of n minus 2 comma n and 2 comma n plus dash dash dash. This way we are going to have n minus 1 pairs, when where the pair is of the form LCM of n minus a comma n plus LCM of a comma n. So these type of n minus 1 pairs we have. Now what is the special thing about these pairs? Now, so overall the right hand side can be represented like this. So the right hand side would be summation I starting from 1 to n minus 1 LCM of I comma n plus LCM of n minus I comma n. So this is what we have to calculate. Now there is something special about these pairs. Let me show you what is special about these pairs. Now see, these two pairs can be represented like this. Now since, as we all know, the GCD of two number, the LCM of two number is multiplication of them divided by their GCD. So LCM of I comma n is this one, and LCM of n minus I comma n is this one. Now in my number theory course, we have already seen the GCD of AB and GCD of A minus B comma B is same. So GCD of IN and GCD of n minus I comma n is same. This we have already covered as well as proved in the number theory course playlist. So you can go and watch the lecture where I have talked about the Euclid algorithm to calculate GCD. In that lecture we have already seen that these two have same GCD. So I can replace the second denominator by the first because they have the same GCD. Now if you see, the denominators are same, so we can add the numerators. If you add the numerators, you are gonna get this expression. So basically now this expression evaluates to this. Now we have to evaluate this expression instead of this. right? So make sure that you understand each and every single step that we have took to derive this expression. This expression still requires n log n time. All you have to do is evaluate this, divide the right hand side by 2 and add n to it, and you get the solution. But the problem is the overall time still is n log n, because we are running a loop from 1 to n minus 1, and each time calling the GCD function, which again takes log n time. So the overall complexity still is n log n. We haven't improved on the time complexity yet. So let's do that. Let's improve the time complexity. Now we already know that. Let me just check one thing. Yeah, good. Now we have to evaluate this expression, but this expression can be evaluated or changed into certain another expression which requires less time to compute solution. So let's do that. Now see, on the right hand side, what I've done, I've taken one n out of this and nothing special. Okay, just taken out one n out of it, and now I'm evaluating this. So what is gonna happen here? See, I'm running a loop each time I'm calculating GCD, but the problem is, as we were studying let me show you just a second. In the number theory course series, I think we were solving some problem Euler transition function and GCD sum. I think this was the lecture or something like, yeah, this is the lecture, I think, in which we talked about that how GCD of certain number with n remains same. So we are running a loop from 1 to n minus 1, each time calculating its GCD with n, but there are many numbers which are having the same GCD, like for d is equals to 1, that is, suppose first thing, GCD is always going to be divisor of n, right? So these are the divisors of n. Assume n is 12, so I'm going till n minus 1, that is 11. That is why 12 is not included, because 12 is one of the divisor of 12, of course, but 12 is equals to n, and we are only going till n minus 1. Now see here, the GCD is always going to be divisor of n. So here what I'm showing you is how many numbers are there from 1 to 11 which are having GCD 1 with 12, and there are 4 numbers, I think 1, 5, 7 and 11, I guess. These are the numbers which are having GCD 1 with 12. So there are 4 numbers which are having GCD 1. Now there are 2 numbers which are having GCD 2. There are 2 numbers which are having GCD 3. There are 2 numbers which are having GCD 4, and there is 1 number which is having GCD 6. Now instead of running a loop from 1 to n minus 1, what I can do, since GCD is only going to be the divisor of n, I can run a loop for divisor of n instead of running from 1 to n minus 1. And we already know that we can calculate the divisor of n in square root of n times. So I'll be running a loop only for divisor of n, and then if the divisor d, for each divisor I'll be calculating how many numbers are there which are having GCD equal to d. For example, for d is equals to 1, I'll be calculating how many numbers are there from 1 to n minus 1 which are having GCD 1 with 12. So in that case, the solution would be count remains, count tells you the number of elements which are having GCD d with n. Now these many numbers are there, so the total contribution in this sum would be, suppose there are 3 numbers, I mean, let's go with this, there are 4 numbers which are having GCD 1 with 12, right? So n by 1 would be added 4 times. When I is equals to 1, GCD of 1 and 12 is 1, so of course 12 by 1 would be added 1 time for 1, again for 5, again for 7, again for 11. So how many times it is being added? 4 times, which is equal to the number of element having GCD equal to d. So for each divisor, I'll be counting how many integers are there from 1 to n minus 1 which are having GCD d, and this is represented by count, and their contribution would be count times n by d, because if their GCD is d, they will be divided by n would be divided by d. And how many times we'll be doing that? Of course, the number of times we are getting the number of elements which are having GCD d. And this count, how can we calculate that? Well, if you go back to this lecture, I think this is that lecture, not exactly sure. You can check out all of the lectures of Euler Stoichkov function, but I think, yeah, this is the lecture in which I have already told you how you can calculate number of elements starting from n1 to n-1, which are having GCD d with n, and that is phi of n by d. We have already evaluated this formula, so count would be replaced by this, and now all we have to do is evaluate the right hand side only on divisor of n. Now how does it help us? See, initially we were required to calculate GCD. First thing, here we don't need to calculate GCD, but we need to calculate phi. So first of all, what we would be doing, we'll be pre-computing phi from 1 to 10 power 6, because in the input n can be as large as 10 power 6. So all we have to do is calculate GCD, I mean ETF or Euler Stoichkov function or phi function, evaluate from 1 to 10 power 6. This you can do using sieve, and the complexity would be n log n. Now instead of running loop from 1 to n-1, we would only running loop till square root of n, because till running a loop from till square root of n, we can calculate all of the divisors of n, and so the overall complexity of this would be square root of n. So yeah, of course, don't forget the pre-processing time, which is n log n. That would be done only once. For each query you have to run this loop. So for each query you can answer in square root of n times. So you see, we have improved from n log n for per query to square root of n per query, right? So using this expression you can calculate, you can evaluate the right hand side in square root of n time. Now we are going to further improve the running time. And how? Of course, we are going to make the running time big O of 1, that is, in constant time we are going to answer each query. So now we will see how we can improve the running time from square root of n to big O of 1. Now for that, what we'll be doing is this. Now let's evaluate for n is equals to 12 the right hand side. Let's only evaluate the right hand side, because the overall complexity is square root of n is because of this expression. So let's evaluate this expression on n is equals to 12. Now if you evaluate this expression on n is equals to 12, this is what you are gonna get. First divisor is 1, so of course 12 by 1 times 12 by 1, then for 2, for 3, for 4, for 6, and for 12. Now if you evaluate this expression on every divisor of n, what you will get is this expression. And now there's something special in this expression which is going to help us reduce the overall time complexity. See, whenever you are going to solve some problem, there are very little information, little observation which help you reduce the overall time complexity, or even solve some problem, solve problems in many cases. So now see here, yeah, now see, we need to evaluate phi or Euler Stoichkov function on 1, 2, 3, 4, 6, and 12. Can you find certain relation between these number and 12? If you observe it carefully, you'll find that 1, 2, 3, 4, 6, and 12 actually are divisor of n itself. Even though we are evaluating on n by divisor, it is still coming out to be all of the divisors of n. And why is happening, and why this is happening, is that if d is divisor of n, n by d is also divisor of n. That is why inside phi, even though we are only running a loop on divisor of n and applying phi on n by d, not on d, still inside phi we are only getting divisor of n, because again, if d is a divisor of n, n by d is also a divisor of n. So all we have to do is evaluate, instead of evaluating on n by d, we can actually evaluate them on d, because of course that would be the same thing, because n by d is also divisor of n. So instead of running a loop and evaluating phi on n by d, we are going to evaluate this on d. So the right hand side expression now becomes this. And remember, after evaluating this expression, we need to remove this, because if you remember from the previous slides, we have to evaluate this expression, we have to evaluate this expression somewhere around this, only till n-1. We don't have to evaluate it on n. So what is happening here, this was 7th slide, yeah. So what is happening here, we are also evaluating this on n is equals to, when you evaluate this expression on n is equals to, d is equals to n, this is what you are gonna get. And that is why we need to, after evaluating this expression, we need to remove 1. Why 1? Because phi of 1 is 1 and 1 times 1 is going to be 1, and this is the expression, this is the term that we don't want, because we don't want to evaluate this on d, and d is equals to n, and on d is equals to n, this is what we are getting. So after evaluating this, we are going to subtract 1 from it, because of phi of 1 times 1, and phi of 1 is 1, so 1 times 1 is 1. So after evaluating this expression, before multiplying with n, we would remove 1 because of this. Now all we have to do is evaluate this expression, but you can see again we have to run a loop for divisors to find the divisors of n, and that again will cost us square root of n time. But this thing we can already calculate. And how we are going to do that? See, for each number n, what I have to do, for each divisor of that number, I have to add d times phi of d, right? For each number n, what would be the solution? Solution would be the sum of d times phi of d for all of the divisor of that number. So what we are going to do, we are going to pre-calculate all of this, so we don't have to calculate this on again and again. And how we are going to do that? Let me show you. Now see, first of all, we'll pre-calculate phi. Phi of 1 is 1, phi of 2 is 1, phi of 3 is 2, and so on. First we will calculate phi using what was it? Using sieve method in n log n, and then we are going to calculate this. We are going to pre-calculate this whole expression. How we are going to do that? See, 1 times phi of 1 will be added to all of the numbers which are having 1 as their divisor, right? So what are the numbers which are having 1 as their divisor? Remember, for each number n, if d is their divisor, then d times phi of d will be added into that, right? Because we are pre-calculating. So 1 times phi of 1 will be added to all of the number which are having 1 as their divisor. So now you see, all of the numbers starting from 1 to 10, all of them are having 1 as their divisor. That is why 1 times phi of 1 is added to all of those. Now let's go to 2. Now 2 times phi of 2 would be added to all of those numbers which are having 2 as their divisor. So starting from 2, 2 would be added to 2, 4, 6, 8 and 10. So these will be turning to 3 because I'm adding 2 times phi of 2 to all of these numbers. Now I'll be going to 3. Now 3 times phi of 3 would be added to all of the number which are multiple of 3, because 3 will be their divisor. Now starting from 3, 3, 6 and 9. In the result 3, 6 and 9, I'll be adding 3 times phi of 3. So 3 times phi of 3 will be added here, here and here. Similarly for 4, 4 times phi of 4 would be added to all multiples of 4. So 4 times phi of 4 would be added to here and here. So see, so using this pre-computation, we'll calculate the result. So what is happening here? You see, 4, how many divisors does it have? 4 is having divisor 1, 2 and 4. So here we have added all of them. Since 4 is having divisor 1, 2 and 4, so 1 time phi of 1 should be added into this, 4 times phi of 4 should be added into this, and 2 times phi of 2 should be added into this as well. So if you see, we have already added all of those numbers here, because when we were calculating for 1, we have added here 1 times phi of 1, where we were calculating for 2, we have added 2 times phi of 2, and similarly when we were pre-processing for 4, we have added 4 times phi of 4 here. So after that, result of n would store actually this whole expression. So now we can use this information to solve the problem in constant time. Let's first see here LLI result. So LLI is long int, basically 64-bit integer. Now result array would store the result, and I mean the pre-processed part, and phi is of course to store phi of every number. Now here if you see here, I'm REP is a function, I mean REP is a for loop that runs from 1 to mx. Now mx is 10 to the power 6, so basically we'll be calculating phi till 10 to the power 6 using method of sieve, so it would take n log n time, and this is here that we are calculating phi of all numbers from 1 to mx, which is 10 to the power 6. I've already explained how to calculate this. Just a second. I've already explained that how you can calculate phi function from 1 to n in n log n time in the lecture 19 of number theory course. So this is what is happening here, and after that we are running our loop from 1 to mx to pre-process this. As you can see, for each multiple of I, for each I from 1 to 10 to the power 6, for each multiple of it, in that we are adding I times phi of I, because I would be divisor of that number j, and that is why here we are again using sieve method to calculate this, and the overall complexity of this would be again the same, that is of sieve. So pre-processing time doesn't take more than n log n time. After that, how you calculate result? Of course, res of n contains the pre-processed this part, and from which we have to subtract 1, so that is why result of n minus 1, and then times n because of this, then divide by 2 and plus n, then divide by 2 and then plus n, that is your result. I'll be putting the link of this code in the description of the video, so that you have idea how to or you can use it as the reference. So this was all for this lecture, and you have, if you have any doubt or query, of course you can ask in the comment section. So thank you guys for watching, and till the next video drops, keep coding. Thank you.